Hey friends, we are back. 3.5. We're going to talk about all things hearing. So the different parts of the ear and how you're able to process your auditory information. Let's get started. Here we go. We got some learning targets. This is shorter today. We're just talking about auditory sensation and perception. So we're going to describe the hearing process, talk about where transduction happens, and then talk about specialized pathways in the brain for each of the senses, specifically the hearing process. Okay, so we have different frequencies, aka pitch, right? So frequency is the dimension of frequency is determined by the wavelength of sound measured in hertz or Hz. So this is the pitch. So how high, how low, sharp or flat, right? Humans can hear sounds of frequencies from about 20 hertz to 20,000 hertz. Hearing is best around 3,000 to 4,000 hertz, or human speech is centered. So a higher frequency means a higher pitch of sound, and we can see that if we're looking at our different waves here at the bottom. We see that the wavelength is shorter between the tops of the purple wave as opposed to the red. So the purple wave is going to have a higher pitch or higher frequency than the red wave. But these are sound waves, right? Not light waves. Intensity, aka loudness. So this is the amount of energy in a wave, and it's determined by amplitude, aka the perceived loudness. And loudness is measured in decibels, not decimals. Bulls with a B. Okay, let's look at the different parts of the ear. So let's start with the pinna off here to the left. This is the part of the ear that you can see. So this is your actual outside ear. This is considered the outer ear. Like you can see right here, this is the outer ear. And from the outer ear, you can have access to the auditory canal, right? So some of y'all put Q-tips in here to get the earwax out. Not good, don't use your Q-tips. The auditory canal leads to the eardrum, which is just a small piece of tissue that separates the auditory canal from the middle and the inner ear. This can be ruptured, this can be damaged. It can heal back, but when it heals back, there's scar tissue with it. And so when you have a buildup of scar tissue, that will affect your hearing. With our middle ear, we have the ossicles, or the tiny bones. And they are the hammer, the anvil, and the stirrup. Stirrup actually looks like a stirrup. Okay, we have our tympanic cavity, because the eardrum is also called the tympanic membrane. Just FYI, we're gonna write that on our paper when we draw this together. Yay! Just like we drew the eyeball. Okay, and these ossicles are these three tiny bones, the hammer, the anvil, and the stirrup. They lead to our semicircular canals. Why do you think they're called semicircular? Because they look just like that. Okay, this is where a lot of our balance is dealt with. So if you are experiencing lack of balance due to maybe like an ear infection or a lot of fluid in your ear, that's because of your semicircular canals, and that is linked with your cerebellum, right? That also helps us with our balance, movement, and coordination. And then if you kind of look below the semicircular canals, you see what looks like almost a snail. It's kind of gross. But this is your cochlea, okay? And it's all curled up like that. Like you could pull it out and you could lay it flat, but it's all curled up nicely in your ear. And this is your inner ear. Your semicircular canals and your cochlea, these are your inner, this is considered your inner ear. Inside there, you have the basilar membrane, which is just kind of like this nice fluid. And in that, you have what are called your hair cells. And as those are going to vibrate, depending on the amount of sound waves or the intensity of the sound waves that are coming into your ear. And that information is going to get sent to your auditory nerve, which is off the back of the cochlea that travels to the brain. Auditory nerve sends it to the thalamus and then the auditory cortex. So we're going to draw this, and when we draw it together, it's going to look probably a little less intense, but I need you to know the different parts of the ear and what section they're included in. So the pinna, is that the outer ear? Yes. 3 tiny bones. Eardrum, is that the middle ear? Yes. Inner ear, your semicircular canals, and your cochlea, and all of that fun stuff. The cochlea. So this is a coil. Like we said, it looks like a snail. Bony, fun. Fluid-filled tube. That's your basilar membrane. In the inner ear, that transduces, that's where your transduction happens. Remember, that's on our blue chart. Sound vibrations to auditory signals. So remember, our brain does not process sound waves. It's got to get sent, it's got to get converted into something that we can process. And so that happens in the cochlea. See, look in the back, the little snail looking thing. Now, theories for hearing. Just like we had theories for color vision, we've got theories for hearing, right? We have the frequency theory. So this theory states that the rate of nerve impulses traveling up the auditory nerve matches the frequency of the tone, thus enabling us to sense pitch. So that's one theory here. And again, when we review these in class, I'm going to go a little bit more into detail and show you kind of the pros and cons of each theory. Now we have another one. This is different. This is place theory. So you can see that frequency theory deals with frequency. Place theory is going to talk about like specific places, right? So place theory suggests that the sound frequencies stimulate basilar movement or stimulate the basilar membrane at specific places, resulting in perceived pitch. Okay, so I will show you a video to explain this, but place theory is all about the different places that the basilar membrane is stimulated, and that's going to result in perceiving a certain pitch. So far we've got frequency theory and place theory. Localization of sound. So you've got 2 ears, right? And in most cases, in most of our cases, probably both of them work. Because we have 2 ears, sounds that reach one ear faster than the other make us localize the sound. So for example, if you're more, maybe you're in class and I'm standing on your left side, so your left ear is closer to me, that's going to help you localize the sound in the fact that, oh, the sound is coming from Miss Thompson who's on the left side of me, because that sound is hitting your left ear first before it has to travel around to the right ear. So this allows you to figure out like, oh, where is that sound coming from? And it allows you to put a location behind the sounds that you're hearing. Hearing loss, because this is a thing. Why do we have hearing loss? We have a couple different kinds. Just as you drive a new car off the lot, it depreciates in value due to its use. Your hearing ability decreases with use, right? This is why usually older people have more poor of hearing than younger people. So we have noise-induced hearing loss. So the progressive, so in time, inability to detect higher frequency sounds due to damage in the hair cells accrued over time and with use. So I'm going to talk about the hair cells more in class, but these are what look like grass in your cochlea, in your basilar membrane, and they vibrate as sound comes in, right? So the more intense the sound is coming in, so let's say you put your headphones in and you blast that music, those hair cells are really, really vibrating, as opposed to if you were listening to your music on a lower volume. And so if you continue over time progressively to listen to your music very, very loudly, those hair cells like are vibrating a lot over time. And so the more that they vibrate or the more that they move back and forth, they start to kind of wear down to where if your hair cell when you're younger is like this length, by the time you're older, it might be smaller, right? And the smaller it is, it's harder for it to vibrate and detect that sound intensity. So this can be something from noise induced. And so you see this in people that have not taken care of their ears. Maybe they've been around a lot of loud music, or people who've tried, but they just have a career where they're around a lot of loud noises, airplanes, trucks, machines, whatever. Generally, any sound loud enough to produce the ringing in our ears causes some damage. So when your ears ring, this lets you know like, hey, you're hurting. Your ears are like, hey, you're hurting me. please stop, right? So this is why maybe after you go to a concert and you come home and your ears are ringing, you've damaged them a little bit, okay? And if you continue to do that over time, you could have hearing loss at an earlier age than someone who has taken care of their ears a little bit better. Okay, high intensity or loud sounds can actually tear off the hair cells from the inner ear. So that's what I was talking about before. Now there's another kind. Conduction deafness. So this is hearing loss caused by damage to the mechanical system that conducts sound waves to the cochlea. So this is like a mechanical issue. This isn't something that you wore down over time. This is an issue with the mechanics of your ear. This could be potentially corrected with surgeries or hearing aids. We also have sensory neural deafness. So this is hearing loss caused by damage to the cochlea's receptor cells or the auditory nerve, also called nerve deafness. So this is also an issue, but this isn't like with the mechanics of the sound waves reaching the cochlea. This is where we're dealing with the receptor cells, and so or the auditory nerve of taking that information to the brain. Sensory neural deafness, this is a permanent condition, as opposed to conduction deafness that may be able to be corrected. Sensory neural deafness would be permanent. Now, cochlear implant, because this is a thing, you can get a sound processor put in, or you can actually get an internal implant in the cochlea. So a cochlear implant is a small, complex electronic device that can help to provide a sense of sound to a person who is profoundly deaf or severely hard of hearing. An implant does not restore normal hearing, though. Instead, it can give a deaf person a useful representation of sounds in the environment or help him or her to understand speech. So this is just something that helps. It's not able to completely restore or completely solve the problem. And remember, our senses go beyond just hearing or just sight, right? Even if you're able to maybe get more of that information in, it still doesn't mean you're able to process exactly what you're hearing. So I need you to keep that in mind when we're talking about sensation and perception. Just because you can hear or see or smell doesn't mean that that information can be processed or perceived. And so that's kind of the issue here. We might be able to get more of those sounds in, but that doesn't mean we're able to process those sounds correctly. Okay, so this is our last slide here. So hopefully we know the different parts of the ear, what they do, and some of the theories behind hearing and hearing loss. And we'll talk about some of these in class the next time we see you. Go into a little bit more detail. We'll draw the ear together, and I'll answer any questions that you have. And maybe do a hearing test or two. Thanks, guys. Make sure you take your notes.